This is Jeremy Clark of JeremyBytes.com, and today we're going to continue our look at C# generics, this time by looking at generic constraints. As a reminder, generics are classes, structures, interfaces, and methods that have placeholders, type parameters, for one or more of the types that they store or use. In part 1, we saw how generics are very common in collections such as list of T. In part 2, we took a look at an iRepository interface that allowed us to create a single interface that would work with multiple types. And in part 3, we saw how we could use generic type parameters as return values and parameters for methods so that a single method would work in a variety of situations. And along the way, we've seen the benefits of generics. This includes type safety, where we know exactly what types we're dealing with because they are strongly typed. It also benefits us with performance, so we don't have to deal with boxing value types to reference types and unboxing them in order to use them. And it also helps us with flexibility and reuse. We've seen how we can reuse these classes, interfaces, and methods in a variety of different situations because they work with different types. Now, it is difficult to come up with a situation that will work with any type in the C# system. Usually, we're dealing with something a little bit more specific, and this is what generic constraints allow us to do. They allow us to limit the particular types that will work with our class, interface, or method. Now, in part 3, we saw when we created our factory method, we put a class constraint on it. What the class constraint specifies is that T, whatever type we're using, must be a reference type. And when we were using that code, we were using the as statement, which only works with reference types. Now we can go the other way as well and specify a constraint of struct. In this case, T must be a value type. There's also times where we don't care whether we're using a reference type or a value type, but we do care about a constructor. So we can use the new constraint to specify that this type must have a no-parameter constructor. So if we try to provide a class that does not have a no-parameter constructor, the build will fail. And we can also add constraints that T must descend from a particular base class or implement a particular interface. When we have constraints like this, it frees us up to use some additional features inside of our methods, classes, and interfaces. We'll take a look at a couple of these in examples so that we have a good idea of how they work. Now there is one other thing that we want to look at, and that is the default keyword. We do have a problem because value types and reference types have different base states that we want to set them to. For reference types, we generally want to set the object to null. So if we say default T, where T is a reference type, then that will result in null. But we can't set value types to null, so what happens there? Well, default T, where T is a value type, will set the value to bitwise 0. Now what this means is if we have something like an integer, it will actually be the number 0. But if we have something like a date time, when we set that struct to a bitwise 0, we actually have the same thing as the minimum date time, so it's equivalent to datetime.minValue. The good thing about calling default T is that it will work with either a reference type or a value type. So if our method will work with either one of those, we can use this to help us out. So let's flip over to the code where we'll see some constraints in action along with the default keyword. So here we are in Visual Studio, and I've opened up the factory.cs file that we looked at previously. This is our generic factory method called get that returns whatever type we want based on T, the generic type parameter. Now if you remember, we added where T:class way back in part 3. What this does is it specifies that T, whatever type we're using, must be a reference type. Now why did we require that? It's because we're using the as statement. So when we say instance as T, it will try to cast the instance to whatever type we give it, but if the cast is unsuccessful, it will return null. Because it's setting a value to null, it must use a reference type. Now let's see what we can do to get rid of this constraint. Maybe I do want to use this method with value types such as structs as well. So the easy way to do this is to change our as statement into a cast. Now, if we cast the value this way, if it's unsuccessful, it will throw an exception. Now, this may be what we want to do in a production application, but in this case, it would actually change the behavior of this particular method. Previously, this method would return null if it wasn't able to do the cast. Now, it will throw an exception instead. So let's see if we can keep the behavior that we had before. So I'm going to create a new variable called result, and we'll initialize this to null. Then, before we do the cast, we'll check to see if the instance is of type T. If it is, we'll go ahead and do the cast. And then we'll go ahead and return that result. So this is a safer way of doing things because we are checking to make sure that the cast is valid before we actually do it. So that will prevent the cast throwing an exception in this case. But we do still have a problem. If I remove our constraint and try to build, we'll get a build error. And the reason for that is we are trying to assign null to a type T. And again, if T happens to be a struct, a value type, this will be unsuccessful. But notice that Visual Studio is helping us out here. It does tell us the error cannot convert null to type parameter T because it could be a non-nullable value type. But then it gives us a clue. Consider using default T instead. And that's exactly what we'll do. So we'll change this to default T. And now when we build, we do get a successful build. But let's explore this default in a little bit more detail. For this, I'm going to create a unit testing project so that we have something that we can work with. So we'll add a new project, and we'll select a unit test project, and we'll call this generics.test. And I'll add a reference to our generics.common because that has our person class in it, so we can use that in this file. And we'll rename our test class to generics tests. So let's just write a couple tests that show how this actually works. So we'll have a public void, and we'll call this default since we're testing the default keyword. And we're going to start with integer because that's the most straightforward. And we're expecting that the result will be 0 because again, it will just set it to bitwise 0. So I'll create a variable called default int, and we'll set this to default of the integer type. Now, since an integer is a value type, what we can do is we can assert that it is not null. But what is the value we're expecting? Well, we can assert our equal 0 default int. So now let's go ahead and build and open up our test explorer and see what we have here. If we run all, we'll see that this test passes, which means when we use default with an integer, the result is not null, and it actually equals 0, and that's exactly what we would expect. Now let's see what happens when we try this with a reference type. And we'll say public void default of, let's try list. And since this is a reference type, we would expect that the default will be null. Let's go ahead and create a list of person. Now I will need to bring in a couple using statements here, so I'm just going to do control dot to bring in system.collections.generics. And then I'll do control dot again to bring in generics.common, which has the person class in it. And we'll name this default list, and we'll set it to default list of person. And then we'll do some similar asserts, but this time we'll say is null default list, because we expect that since this is a reference type, that the default value for it will be null. And then we can also do an r equal null and default list. Now I'm going to come up here to my test explorer and click this button that says run tests after build. So this way, every time I build my application, it will automatically rerun the tests. And we can see that our results are exactly what we expected. So here it's easy to see what default is doing. When default is working with a value type, such as integer, the result is bitwise 0, which for an integer just happens to be the number 0. For a reference type, like list of person, the default is null. Now things do get interesting when we look at non-numeric value types. Let's see what happens when we use a date time. So we'll create a test method, and this will be public void, and we'll call this default date time is, well, do we know what it is? It's actually min value. Let's go ahead and verify this. So we'll create a date time called default date. And we'll set this to default date time. And then since date time is a struct, we can assert that it is not null. And that should be true for default date. But what is the value? If we say are equal, what do we compare it to? Well, as a reminder, default of value types is a bitwise 0, which means it zeroes out all of the values inside the struct. It turns out if you bitwise 0 all the fields in a date time, you end up with the min value. So we can say datetime.min value and compare that to our default date. And now if we build and look at our unit tests, we'll see that this completes successfully as well. So we've been able to show that default results in a bitwise 0, which in the case of an integer is just 0, and in the case of datetime turns out to datetime.min value. So now that we have a better understanding of how default works, let's go back to our factory and take a look at what we have. So here we're saying tResult equals default t. So if we're working with a reference type like the classes of our repositories, this will be null. But if we use a value type such as an integer or a date time, then result will be a bitwise 0. So default t allows us to reset the value regardless of whether it's a reference type or a value type. And this can be very helpful when we're dealing with generic methods. So we've seen the class constraint in action. If we do require a reference type, we can say where t:class, and that will limit us to only using reference types. And again, the reverse is true. If we need a value type, we can say where t:struct. But we can also specify a particular interface or base class. Let's go back to our test file and just create a method that we can use. So normally I wouldn't put this helper class inside of our tests, but we're just getting a good idea of how constraints work at this point. So I'm going to create a public static class that we'll call helper methods. And what I want to do is create a method that will return the maximum value based on 2 parameters. So this will be a public static method and we'll return type t. And we'll say that this is max of t. And for our parameters, we'll have value 1 and value 2. Now, if I was just coding up a method that would work with integers, I might be tempted to do something like this. If value 1 is greater than value 2, return value 1, else return value 2. And if I was dealing with just integers, this would actually work. The reason why this doesn't work when we just have a generic type parameter is that the greater than sign is not overloaded for every type in the system. So that means if we want to do this type of comparison, we can't just use the greater than sign by default. But what we can do is put a constraint on this to limit it to a particular interface. Now .NET already has something for us. So let me say where t is iComparable, or iComparable depending on what part of the country you're from. Now something very interesting happens when we add this type of constraint. Now if I say value 1 dot, in addition to the 4 methods that we normally have on object, equals, get hashcode, get type, and toString, I also have the method compare_to. Compare_to returns a negative number, a 0, or a positive number depending on which of the items is greater. So I can say value1.compare_to value 2. And if it's greater than or equal to 0, then I know that value 1 is actually the greater value based on this comparison. Now that we have this method in place, let's go ahead and create a couple of tests so that we can see it in action. So we'll say public void max with ints returns higher value. And we'll just create an int value for our result. And we'll say helper methods.max and then pass it in 2 values. So let's pass in 23 and 530. Then all we have to do is compare our results. So we'll say 530 should be the result that comes back. And if we build, our test will automatically run, and we can see that max with ints returns higher value does in fact return true. Now, the reason this works is that int does implement iComparable. In fact, many of the built-in types in .NET implement iComparable so that we can put them in a particular order. And there's a similar interface for iEquatable so that we can see if two values are equal. So let's try one more test that actually uses date-time values. So we'll create a test method, and we'll say public void max with dates returns later date. And for this, I'll create some variables. So we'll create a variable called today, which will be datetime.today. And we'll create one called yesterday, which is datetime.today.addDays -1. So let's get a result from our method. So we'll say helper methods.max today and yesterday. And of course, we would expect that the higher value will be today. So we can compare datetime.today with the result that's coming back. And again, we build our application and we'll see our new unit test come up, and we'll see that max with dates returns later date does in fact pass. Now let's try one more test, this time with our person class. So this will be public void max with person returns, well, I'm not exactly sure what it will return. So let's create person A, which will be a new person, and person B, which will also be a new person. And we'll create a result, and we'll say helper methods.max person A, person B. And we actually have an error. If we look at this, it says the type generics.common.person cannot be used as a type parameter because there's no implicit conversion to system.iComparable. So what this is saying is the person class doesn't implement the iComparable interface. And if we actually go to the definition, we'll see that it doesn't implement any interfaces at all, and it just descends from object. So because of that, the generic constraint prevents us from using the person object with this particular method. And that's exactly what we want. We don't actually have a way to specify which person is greater than another person. And if we did come up with some criteria, for example, someone makes more money, someone has a higher education, someone has a bigger family, we could actually implement the iComparable interface on our person class and specify greater than, less than, or equal to based on those particular criteria. But since this won't work, we'll just have to comment out the whole thing. And let's do a final build and let our tests run one last time. So we've seen a couple of things here. We have seen generic constraints in action. In our max method, we did put a constraint on saying that T needs to implement the iComparable interface. Because of this, it does work with int and datetime, which do implement the interface, but it does not work with person, which does not implement the interface. And we also saw how the default keyword works. If we don't know if we have a class or a struct, there's no way for us to assign null or zero explicitly because it depends on what the actual type is. But if we use default T, then it will return the appropriate setting for that particular object. And that works really well in situations where we can work with either value types or reference types. And this brings us to the end of looking at generic constraints. Now, obviously, there's a lot more to explore here. You can have multiple generic type parameters and different constraints on each parameter. And you can also combine constraints. So you can specify it must be a class that has a no parameter constructor that implements a particular interface. Now, how detailed we get with this really depends on what our needs are. If we find ourselves being too specific, then maybe a generic type isn't the right choice for us. But if we can find that the method, interface, or class can apply in a variety of different situations, constraints can help us get exactly the functionality that we need. And this also brings us to the end of our discussion on C# generics. There are some more advanced features that we could talk about as well, such as covariance and contravariance, but I'll leave that up to you to explore on your own. To get the downloads for this series, check the video notes for the links to the code. And for more information, feel feel free to visit www.JeremyBytes.com.